Hello there, and welcome to the Sleepy Science Channel. Tonight we'll be embarking on a journey beyond our world, into the vast expanse where humanity has dared to venture. A place of wonder, of achievement, and of dreams made real. We will explore the extraordinary history of space travel, from the first tentative launches to the grand visions of tomorrow. Above us, beyond the thin veil of atmosphere, lies a realm that once seemed impossible to reach. Yet through ingenuity, courage, and persistence, we have crossed that threshold. We have walked on other worlds, built homes in orbit, and sent our creations to the edge of the solar system and beyond. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here, too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the gentle story of our journey into space to carry you softly into sleep. Let's begin. The first dreams of flight. Long before rockets touched the stars, humans dreamed of flying. Ancient myths tell of heroes strapping on wings, of chariots drawn by celestial horses, of journeys to the sun and moon. These were more than stories. They were the first expressions of a yearning that lived deep in the human heart, a desire to rise above the earth, to see what lay beyond the horizon of the sky. In China, legends spoke of Chang'e floating to the moon. In Greece, Icarus flew too close to the sun. These tales, though impossible in their telling, held a seed of something real. The belief that one day, somehow, humans might leave the ground behind. For centuries, that dream seemed forever out of reach. Birds soared freely, while humans remained earthbound, watching with envy. Yet the desire never faded. It smoldered quietly through generations, waiting for the knowledge and tools that would make it possible. The night sky was not just something to admire. It was a destination, distant but calling. Every star, a possible harbor. Every planet, a world that might one day welcome footsteps. The birth of rocketry. The story of space travel begins not with grand machines, but with simple tubes of powder. Rockets, in their most primitive form, were invented in China more than 1,000 years ago. These early rockets were little more than fireworks, bundles of gunpowder attached to arrows, launched to frighten enemies or celebrate festivals. They rose on plumes of fire and smoke, unpredictable and dangerous, but they proved something fundamental, that controlled explosions could lift objects into the air. For centuries, rockets remained curiosities, tools of war or spectacle, nothing more. But in the late 19th and early 20th centuries, a handful of dreamers began to see their true potential. In Russia, a schoolteacher named Konstantin Tsiolkovsky filled notebooks with calculations, imagining rockets that could escape Earth's gravity entirely. He never built a single one, but his equations laid the foundation. In America, Robert Goddard launched the first liquid-fueled rocket in 1926, a small device that rose only a few dozen meters before crashing into a cabbage patch. It seemed insignificant at the time, yet it was the beginning. In Germany, a young engineer named Wernher von Braun dreamed of sending rockets to the moon. His work, tragically, was first used for destruction during the Second World War. But after the conflict ended, his knowledge would help ignite the space age. The rocket, once a weapon and a toy, was about to become something far greater. A vessel for exploration, a bridge between Earth and the cosmos. The space age dawns. On the 4th of October, 1957, a small metal sphere climbed into the sky above Kazakhstan. It was no larger than a beach ball, weighing less than 200 pounds, and it carried nothing but a simple radio transmitter. Yet, its impact on history was immeasurable. This was Sputnik, the first artificial satellite, and as it circled the Earth every 96 minutes, its steady beep echoed across the world. Humanity had, for the first time, placed an object in orbit. The space age had begun. The achievement sent shockwaves through nations. In America, people looked upward with a mixture of wonder and concern, realizing that if satellites could orbit the Earth, so too could weapons. A race began, not just for scientific achievement, but for dominance in this new frontier. Within months, more satellites followed. Sputnik 2 carried a living passenger, a dog named Laika, proving that life could survive in the void. Though Laika did not return, her journey marked another threshold crossed. The quiet beep of Sputnik's radio faded after 3 weeks, but its legacy endured. The sky was no longer an unreachable ceiling. It had become a highway, a place where human creations could travel freely. The dream of reaching the stars no longer seemed like fantasy. It was becoming real, one small step at a time. The first human in space. Less than 4 years after Sputnik, on the 12th of April 1961, a young Soviet cosmonaut named Yuri Gagarin climbed into a capsule atop a towering rocket. He was 27 years old, a pilot with a calm demeanor and an easy smile. What lay ahead of him, no human had ever experienced. The rocket ignited, and the ground shook as it rose into the sky, carrying Gagarin away from everything familiar. Within minutes, he crossed the threshold of space, becoming the first human to leave the Earth. Gagarin's flight lasted only 108 minutes, a single orbit around the planet before his capsule descended back to the surface. But in that brief time, he saw what no one before him had witnessed. The curvature of the Earth, the thinness of the atmosphere, the blackness of space punctuated by the brilliance of stars. He radioed back simple observations, describing the beauty of his home world from above. His calm voice carried across the void, a message of triumph and wonder. When he landed safely in a field, Gagarin became an instant hero. His achievement proved that humans could survive in space, that the journey beyond Earth was not a death sentence, but a beginning. He had opened a door, and now others would follow through it. The dream of spaceflight was no longer just for scientists and engineers. It was for everyone, a shared accomplishment that reminded the world of what humanity could achieve. America joins the race. The success of Yuri Gagarin spurred America into action. Less than a month later, astronaut Alan Shepard climbed into a tiny Mercury capsule and rode a rocket into space. His flight was brief, just 15 minutes, and it did not orbit the Earth. But it was a start. America had joined the space race, and the competition intensified. President John F. Kennedy, inspired by the challenge, stood before Congress and declared a bold goal. America would send a man to the moon and return him safely before the decade's end. It was an audacious promise. At the time, American rockets had carried a man into space for only a quarter of an hour. The technology to reach the moon did not yet exist. The journey would require spacecraft far larger and more complex than anything yet built, navigation systems of unprecedented accuracy, and the courage of those willing to risk everything. Yet the promise was made, and the work began. Throughout the 1,960 seconds, both America and the Soviet Union pushed the boundaries further. Cosmonauts and astronauts spent longer in orbit, learning to live in weightlessness, to maneuver their spacecraft, to step outside and float in the void. Each mission built on the last, solving problems, refining techniques, inching closer to the ultimate goal. Space was no longer a place visited briefly and then fled. It was becoming a realm where humans could work, survive, and prepare for even greater journeys. Walking in the void. On the 18th of March 1965, Soviet cosmonaut Alexei Leonov opened the hatch of his spacecraft and floated outside. Tethered only by a thin cord, he became the first human to walk in space. For 12 minutes, he drifted in the silence, surrounded by the infinite blackness, the Earth turning slowly below him. It was beautiful and terrifying. The emptiness stretched in every direction, and only the thin fabric of his suit separated him from the vacuum. Leonov's spacewalk was not without danger. His suit inflated in the vacuum, making it stiff and difficult to move. When it came time to return, he struggled to fit back through the narrow airlock. For a moment, it seemed he might be trapped outside, doomed to float away. But he managed to release some pressure from the suit, compressing it enough to squeeze through. When the hatch finally closed behind him, he was drenched in sweat, exhausted but alive. Just months later, American astronaut Ed White performed his own spacewalk, floating outside Gemini 4 for 23 minutes. He described it as the most peaceful experience of his life, a feeling of total freedom. To leave the spacecraft and trust entirely in the fragile equipment keeping you alive required a kind of faith that few possess. Yet these early spacewalks proved it could be done. Humans could work outside their vessels, repair equipment, build structures. The ability to walk in space would become essential for everything that followed. The moon beckons. As the 1,960 seconds progressed, the goal of reaching the moon drew closer. NASA developed the Saturn V rocket, a towering giant that stood as tall as a 36-story building. Its engines produced more thrust than any machine before it, powerful enough to shake the ground for miles around when it launched. The spacecraft that would carry astronauts to the moon, the Apollo Command and Lunar modules, were built and tested. Every component was scrutinized, every procedure rehearsed. In December 1968, Apollo 8 carried 3 astronauts beyond Earth's orbit for the first time. They did not land on the moon, but they circled it, seeing its ancient, cratered surface up close. They looked back at Earth, a fragile blue marble suspended in the darkness, and read from the Book of Genesis to an audience of millions watching from home. It was Christmas Eve, and for a moment, the wonder of the journey transcended politics and competition. It became something shared by all humanity. The success of Apollo 8 proved that the moon was within reach. The technology worked. The navigation was precise. The astronauts could survive the journey. Now, all that remained was the landing itself, the moment when human feet would touch another world for the first time in history. That moment was less than a year away, and the world waited with anticipation. One small step. On the 20th of July, 1969, 2 men descended toward the moon's surface in a fragile spacecraft. Neil Armstrong and Buzz Aldrin piloted the lunar module Eagle. As it separated from the command module orbiting above, the descent was tense. Alarms sounded as the computer became overloaded. The planned landing site was covered in boulders, forcing Armstrong to fly manually, searching for a safe place to set down. Fuel ran low. Mission Control watched nervously as the seconds ticked away. Then, finally, Armstrong's voice crackled over the radio. "The Eagle has landed." 6.5 hours later, Armstrong opened the hatch and climbed down a ladder to the surface. The entire world watched on television as his boot touched the lunar dust. "That's one small step for man," he said. "One giant leap for mankind." The words were simple, but they carried the weight of every dream, every calculation, every sacrifice that had brought humanity to this moment. We were no longer confined to Earth. We had become travelers among worlds. Aldrin joined him on the surface, and together they spent 2.5 hours outside, planting a flag, collecting rocks, and photographing the desolate landscape. They moved in, slow, bounding leaps, adapted to the moon's weak gravity. The sky above them was black, even in daylight, because the moon has no atmosphere to scatter light. They could see Earth hanging in that darkness, a brilliant blue oasis in the void. When they climbed back into the lunar module and rejoined Michael Collins in orbit, they carried with them not just moon rocks, but proof that the impossible could become real. The Apollo Legacy 5 more Apollo missions successfully landed on the moon after Armstrong and Aldrin's historic journey. Each explored different regions, from the rolling hills of the Fra Mauro Highlands to the towering mountains of the Taurus Littrow Valley. Astronauts drove across the surface in lunar rovers, lightweight vehicles that left tracks in the ancient dust. They set up experiments, drilled into the lunar soil, and brought back hundreds of pounds of rock samples that scientists still study today. Apollo 13, launched in April 1970, never reached the moon. An oxygen tank exploded 2 days into the mission, crippling the spacecraft. The 3 astronauts aboard, Jim Lovell, Jack Swigert, and Fred Hayes, faced a harrowing choice: turn around immediately and risk running out of life support, or continue around the moon and use its gravity to slingshot back toward Earth. They chose the latter, enduring days of cold, dwindling resources, and uncertainty. Their survival, achieved through ingenuity and teamwork between the crew and mission control, became one of spaceflight's most celebrated triumphs. Not a successful landing, but a successful rescue. The final Apollo mission, Apollo 17, launched in December 1972. Astronauts Eugene Cernan and Harrison Schmitt, the first scientist astronaut to visit the moon, spent 3 days exploring the Taurus Littrow Valley. When they climbed back into the lunar module for the last time, Cernan paused on the ladder and spoke into the silence. "We leave as we came, and God willing, as we shall return, with peace and hope for all mankind." Then they lifted off, leaving behind footprints that remain undisturbed to this day, preserved in the airless environment. Humanity had touched the moon, and though we have not returned since, that achievement endures. Skylab and the first space station. With the moon missions complete, attention turned to a new challenge. Could humans live in space for extended periods? Not just days, but weeks or even months? In 1973, NASA launched Skylab, America's first space station. It was enormous, fashioned from the upper stage of a Saturn V rocket, with room inside for 3 astronauts to live and work in relative comfort. Solar panels provided power, and a large telescope allowed observations of the sun impossible from Earth's surface. Skylab's launch nearly ended in disaster. During ascent, a micrometeoroid shield tore away, taking one of the solar panels with it and jamming the other. The station reached orbit but was crippled, overheating from direct sunlight, and with limited power. The first crew, launched 11 days later, faced an unplanned repair mission. They deployed a makeshift sunshade, freed the jammed solar panel, and brought Skylab back to life. It was an early lesson in the resourcefulness required for long-duration spaceflight. 3 crews visited Skylab over the following year, with the final mission lasting 84 days. Astronauts adapted to weightlessness, exercised to prevent muscle loss, and conducted hundreds of experiments. They watched Earth pass below them, photographing weather patterns, cities lit at night, and the delicate auroras that danced above the poles. When the last crew departed in February 1974, Skylab was left empty, slowly descending as atmospheric drag pulled it lower. It finally re-entered the atmosphere in 1979, breaking apart over the Indian Ocean and scattering debris across Australia. Though its life was brief, Skylab proved that humans could thrive in space, preparing the way for even more ambitious stations. The shuttle era begins. On the 12th of April 1981, exactly 20 years after Yuri Gagarin's pioneering flight, a new kind of spacecraft lifted off from Kennedy Space Center. The Space Shuttle Columbia was unlike anything before it. Previous spacecraft were capsules, used once and discarded. The shuttle was designed to launch like a rocket, but land like an aeroplane, reusable and capable of carrying large payloads into orbit. Astronauts John Young and Robert Crippen piloted it on its maiden flight, orbiting Earth for 2 days before gliding back to a runway in California. It was a perfect mission, a new chapter in space exploration. The shuttle fleet eventually grew to include 5 orbiters: Challenger, Discovery, Atlantis, and Endeavour joining Columbia. Over the next 3 decades, they launched satellites, deployed the Hubble Space Telescope, ferried astronauts to space stations, and carried out countless experiments. The shuttle's cargo bay was large enough to hold a school bus, and its robotic arm could grasp satellites for repair or release them into orbit. It became the workhorse of American spaceflight, a familiar sight as it rode twin solid rocket boosters into the sky. Yet the shuttle was not without tragedy. On the 28th of January, 1986, Challenger exploded 73 seconds after launch, killing all 7 crew members, including schoolteacher Krista McAuliffe, who was to have been the first private citizen in space. The disaster grounded the shuttle fleet for nearly 3 years, while NASA investigated and redesigned critical components. Then, on the 1st of February 2003, Columbia disintegrated during re-entry, killing its crew of 7. These losses were reminders of spaceflight's inherent dangers, the thin margins between success and catastrophe. But despite the risks, the shuttle program continued, achieving remarkable successes before retiring in 2011 after 135 missions. Building a home in orbit, while the shuttle flew, plans were being drawn for a new kind of space station, one far larger and more ambitious than Skylab. The International Space Station would be a collaborative effort built by the United States, Russia, Europe, Japan, and Canada. Its construction began in 1998, with modules launched piece by piece and assembled in orbit. Astronauts performed dozens of spacewalks, connecting power cables, installing equipment, and expanding the structure. It took more than a decade to complete. The ISS is massive, about the size of a football field, with habitable space equivalent to a 6-bedroom house. Solar panels stretch out like wings, generating power from sunlight. Inside, astronauts from around the world live and work together, conducting experiments in biology, physics, and materials science. They study how the human body adapts to weightlessness, how plants grow in microgravity, and how flames behave without gravity to shape them. The station orbits Earth every 90 minutes, traveling at over 17,000 miles per hour, high enough that the curvature of the planet is always visible. Living on the ISS requires adaptation. There is no up or down in weightlessness, so astronauts float through the modules, using handholds to pull themselves along. Sleeping happens in small cabins, in sleeping bags strapped to the wall to keep from drifting. Eating requires careful attention. Crumbs and liquids float away, so most food is packaged in pouches. Water is precious and recycled, including moisture from breath and sweat. Even urine is processed and purified, a necessity when resupply missions are months apart. Despite the challenges, astronauts often describe their time on the ISS as profoundly rewarding, a chance to live among the stars and contribute to knowledge that benefits all of humanity. The Mir space station. Before the ISS, there was Mir, a Soviet and later Russian space station that orbited Earth from 1986 to 2001. Mir was the first modular station, assembled over time as new sections were launched and added. At its peak, it consisted of 7 modules, providing space for research, living quarters, and docking ports for visiting spacecraft. Cosmonauts lived aboard Mir for months at a time, and one, Valery Polyakov, spent an astonishing 437 consecutive days in space, a record that still stands. Life on Mir was challenging. Equipment frequently malfunctioned, and repairs were a constant necessity. A fire broke out in 1997, filling the station with smoke and forcing the crew to don oxygen masks. Later that same year, a resupply ship collided with the station during docking, puncturing one of the modules and depressurizing it. The crew barely managed to seal it off in time. Yet despite these crises, Mir endured, and its lessons proved invaluable for future space stations. In the late 1992s, American astronauts began visiting Mir as part of a cooperation program with Russia. These missions fostered collaboration and built trust between former Cold War rivals. When Mir was finally deorbited in 2001, it burned up over the Pacific Ocean, pieces of it falling harmlessly into the sea. It had outlived its intended lifespan by years, a testament to human determination to keep it functioning. Mir's legacy lives on in the ISS, which inherited much of its design philosophy and continues the tradition of international cooperation in space. Robotic explorers. While humans ventured into near-Earth space, robotic spacecraft traveled much farther. These tireless explorers have visited every planet in the solar system, and many have journeyed beyond. In 1976, Viking 1 and Viking 2 landed on Mars, becoming the first spacecraft to successfully operate on the surface of another planet. They tested the Martian soil for signs of life, photographed the rust-colored landscape, and measured the thin, frigid atmosphere. Though they found no definitive evidence of life, they opened the door for future exploration. Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare alignment of the outer planets. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune, sending back stunning images of these distant giants and their moons. Voyager 1 took a different path, flying close to Saturn before heading toward interstellar space. In 2012, it became the first human-made object to leave the solar system, crossing into the region where the sun's influence fades and the space between stars begins. Both Voyagers carry golden records, discs engraved with sounds and images of Earth, messages for any intelligent life that might one day find them. The Cassini spacecraft orbited Saturn for 13 years, studying its rings, its moons, and its atmosphere in exquisite detail. It discovered geysers of water erupting from the moon Enceladus, hinting at a subsurface ocean that could harbor life. In 2017, low on fuel, Cassini was deliberately crashed into Saturn to avoid contaminating its potentially habitable moons. These robotic missions extend humanity's reach far beyond where we can physically travel, sending back knowledge and wonder from the farthest corners of the solar system. Mars rovers. Mars has captivated humanity's imagination for centuries, its reddish hue suggesting both fire and the possibility of life. In recent decades, we have sent a fleet of robotic explorers to wander its surface. In 1997, the Pathfinder mission delivered a small rover named Sojourner, which spent 3 months analyzing rocks and proving that rovers could navigate the Martian terrain. Then came Spirit and Opportunity, twin rovers that landed in 2004. Designed to last 90 days, they far exceeded expectations. Spirit operated for 6 years, and Opportunity continued for an astounding 14, traveling 28 miles across ancient lake beds and crater rims. In 2012, the Curiosity rover, a car-sized robot equipped with 17 cameras and a suite of scientific instruments, landed in Gale Crater. Its mission is to determine whether Mars ever had conditions suitable for life. It has drilled into rocks, analyzed their composition, and found organic molecules, the building blocks of life. In 2021, the Perseverance rover joined Curiosity, landing in Jezero Crater, a site believed to have once held a lake. Perseverance carries a small helicopter named Ingenuity, which has made dozens of flights, proving that powered flight is possible in Mars's thin atmosphere. These rovers are not just machines. They become companions to the scientists who operate them, anthropomorphized and celebrated. When Opportunity's mission finally ended during a global dust storm in 2018, the last message it sent could be summarized as, "My battery is low, and it's getting dark." The world mourned. These rovers are our eyes and hands on another world, patiently exploring, testing, and sending back postcards from the frontier. Each discovery brings us closer to answering the question that haunts every gaze toward Mars. Were we ever not alone? The search for life beyond Earth. One of the most profound questions driving space exploration is whether life exists elsewhere in the universe. Our search has taken many forms. Robotic missions test the soil of Mars and analyze the plumes of water shooting from icy moons. Telescopes search for planets orbiting distant stars, looking for worlds with atmospheres that might contain oxygen, methane, or other gases associated with life. Radio telescopes listen for signals, evidence of technological civilizations trying to communicate across the stars. So far, we have found no definitive proof of life beyond Earth. But the universe is vast, and we have only just begun to look. The discovery of extremophiles on Earth, organisms thriving in boiling springs, frozen tundra, and deep ocean vents, has expanded our understanding of where life might exist. If life can flourish in such harsh environments here, perhaps it can survive in the subsurface oceans of Europa, the methane lakes of Titan, or the ancient riverbeds of Mars. The question is not just scientific, but philosophical. The discovery of even microbial life on another world would transform our understanding of existence. It would mean life is not unique to Earth, but a common phenomenon, perhaps woven into the fabric of the cosmos. And if simple life is common, then the possibility of intelligent life, civilizations like ours, or vastly different, becomes more plausible. For now, the search continues, driven by curiosity and the hope that one day we will find an answer written in the stars. Hubble's eye on the universe. Launched in 1990, the Hubble Space Telescope revolutionized our view of the cosmos. Positioned above Earth's atmosphere, it captures images with a clarity impossible from the ground. Hubble has photographed distant galaxies, glowing nebulae, and the swirling storms of Jupiter. It has measured the rate at which the universe is expanding, pinpointed the age of the cosmos at nearly 14 billion years, and discovered that the expansion is accelerating, driven by a mysterious force called dark energy. One of Hubble's most iconic achievements is the deep field images. By pointing at a seemingly empty patch of sky and collecting light for days, Hubble revealed thousands of galaxies in a region no larger than a grain of sand held at arm's length. Each galaxy contains billions of stars, and many are so distant Their light has traveled for billions of years to reach us. These images remind us of the universe's scale, a vastness filled with more galaxies than we can count, each a potential home to worlds and perhaps life. Hubble has also observed the birth and death of stars, capturing images of stellar nurseries where new suns ignite and supernova remnants where old stars explode. It has tracked comets, studied black holes, and even detected the atmospheres of planets orbiting other stars. After more than 3 decades in orbit, Hubble continues to operate, its discoveries reshaping our understanding of the universe. It is more than a telescope. It is a time machine, showing us the cosmos as it was billions of years ago, and a reminder of how much remains to be explored. The James Webb Space Telescope. In December 2021, the James Webb Space Telescope launched. Destined for a point in space nearly 1 million miles from Earth, Webb is larger and more powerful than Hubble, with a mirror over 20 feet across and instruments sensitive to infrared light. This allows it to peer through dust clouds that block visible light, revealing hidden stars and galaxies from the earliest epochs of the universe. Webb's first images, released in 2022, were breathtaking. It captured the deepest view of the universe ever achieved, showing galaxies that formed just a few 100 million years after the Big Bang. It revealed the atmospheres of exoplanets, detecting water vapor and carbon dioxide on worlds orbiting distant stars. It photographed the pillars of creation, a star-forming region previously imaged by Hubble, in stunning new detail, showing infant stars hidden within the dust. Webb's mission is to explore the origins of the universe, the formation of galaxies, the life cycles of stars, and the nature of planets beyond our solar system. It represents the cutting edge of technology, a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. Each image it sends back is a window into the cosmos, revealing structures and phenomena that challenge our understanding. As it continues its work, Webb promises to answer old questions and pose entirely new ones, pushing the boundaries of what we know. The promise of exoplanets. For most of human history, we could only wonder whether planets orbited other stars. In 1995, that question was answered when astronomers detected the first exoplanet orbiting a sun-like star. Since then, thousands more have been discovered, with new ones announced regularly. They come in astonishing variety. Gas giants larger than Jupiter, orbiting closer to their stars than Mercury. Rocky super-Earths with masses several times our own, and planets that orbit binary star systems, their skies lit by 2 suns. Some of these worlds exist in the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Water is essential for life as we know it, so these planets are of particular interest. Instruments like the Kepler Space Telescope and the Transiting Exoplanet Survey satellite have identified thousands of candidates. Follow-up observations with telescopes like Webb are beginning to characterize their atmospheres, searching for chemical signatures that might indicate life. The diversity of exoplanets suggests that planetary systems are common, and where there are planets, there might be life. We do not yet know if any of these worlds are inhabited, but the search is accelerating. Every new discovery refines our understanding of what makes a planet habitable and brings us closer to answering whether we are alone. The universe, it seems, is full of worlds, each one unique, each one a potential harbor for life. Private spaceflight emerges. For decades, space exploration was the domain of governments, funded by taxpayers and driven by national pride. But in the 21st century, private companies began to enter the arena. SpaceX, founded by entrepreneur Elon Musk, developed the Falcon 9 rocket, designed to be partially reusable. Instead of discarding the first stage after launch, it lands vertically, ready to fly again. This innovation has dramatically reduced the cost of reaching orbit. In 2020, SpaceX's Crew Dragon capsule carried astronauts to the International Space Station, the first time a private company had launched humans into orbit. Other companies are following suit. Blue Origin, founded by Jeff Bezos, has developed rockets for suborbital tourism, offering brief trips to the edge of space, where passengers experience a few minutes of weightlessness. Virgin Galactic operates a spaceplane that reaches similar altitudes. These ventures are making space accessible to more people, not just professional astronauts, but private citizens willing to pay for the experience. Private spaceflight is also enabling new kinds of missions. Companies are planning to mine asteroids for resources, build commercial space stations, and establish infrastructure for future lunar and Martian exploration. This shift from government-led to commercial spaceflight is opening the space frontier in ways that were unimaginable just a few decades ago. The dream of space is no longer limited to nations. It is becoming an industry, a new arena for innovation and enterprise. Returning to the Moon, more than 50 years after the last Apollo mission, humanity is preparing to return to the Moon. NASA's Artemis program aims to land astronauts on the lunar surface by the mid-2022s, including the first woman and the first person of color. Unlike Apollo, which focused on exploration and scientific discovery, Artemis is designed for long-term sustainability. The goal is to establish a permanent presence, building infrastructure that will support extended stays and serve as a stepping stone for missions to Mars. Central to Artemis is the Lunar Gateway, a small space station that will orbit the Moon. It will serve as a staging point for lunar landings, a research laboratory, and a platform for deep space exploration. The gateway will be assembled gradually, with modules contributed by multiple countries. It represents a new model of international cooperation, building on the lessons of the ISS. On the lunar surface, astronauts will explore the South Polar region, an area of particular interest because it contains ice deposits in permanently shadowed craters. This ice could provide water, oxygen, and even fuel, resources essential for sustaining a lunar base. Returning to the Moon is not just about repeating past achievements. It is about building a foundation for the future, creating the technologies and experience needed to venture even farther into the solar system. The vision of Mars. Mars has long been the ultimate destination for human space exploration. It is the most Earth-like planet in the solar system, with a day length similar to ours, polar ice caps, and evidence of ancient rivers and lakes. Though its surface is now cold and dry, with a thin atmosphere mostly carbon dioxide, Mars may have once been warmer and wetter, a place where life could have emerged. Plans to send humans to Mars are ambitious and complex. The journey would take 6 to 9 months, and astronauts would need to spend at least a year on the surface, waiting for Earth and Mars to align favorably for the return trip. This means a mission would last 2 to 3 years, far longer than any human has spent away from Earth. The challenges are immense. Radiation exposure during the journey, the psychological strain of isolation, the need to produce food, water, and oxygen on Mars. Yet the vision persists. NASA, SpaceX, and other organizations are developing the technologies required. Rockets powerful enough to carry the necessary equipment, habitats that can withstand the Martian environment, life support systems that can recycle resources with near-perfect efficiency. The first Mars missions will likely establish small outposts, gradually expanding as more supplies and people arrive. The dream is not just to visit Mars, but to stay, to build a second home for humanity and ensure our survival as a species. Living on other worlds, establishing permanent settlements on the Moon or Mars, will require reimagining how humans live. Everything we take for granted on Earth, breathable air, drinkable water, protection from radiation, must be engineered. Habitats will likely be built using local materials, Martian regolith or lunar soil, possibly shaped by 3D printers, into structures that provide shelter. Growing food in space is another challenge. On the ISS, astronauts have successfully grown lettuce, radishes, and peppers. But scaling this up to feed an entire colony requires solving problems of soil, lighting, and pollination. Hydroponics and aeroponics, methods that grow plants without soil, may offer solutions. Producing enough food to be self-sufficient will take time, and early settlers will depend on shipments from Earth. Psychologically, living on another world will be demanding. Settlers will be far from home, with communication delays of several minutes to Mars and no possibility of rapid rescue if something goes wrong. They will live in confined spaces, surrounded by a hostile environment, yet humans have always adapted to new frontiers, from deserts to polar ice. The settlers of the Moon and Mars will be pioneers, building the foundations of civilizations that may one day thrive independently of Earth. The power of nuclear propulsion, one of the greatest obstacles to exploring the outer solar system and beyond, is the time it takes to get there. Chemical rockets, the kind used for all human spaceflight so far, are limited by the energy they can produce. A journey to Mars takes months, and reaching the outer planets would take years or decades. To shorten these trips, new forms of propulsion are being developed. Nuclear propulsion is one promising option. Nuclear thermal rockets heat a propellant using a nuclear reactor, producing exhaust that accelerates the spacecraft. This method is far more efficient than chemical rockets, potentially cutting the travel time to Mars in half. Nuclear electric propulsion, which uses electricity from a reactor to accelerate ions, offers even greater efficiency for long missions to the outer planets. These technologies are not just theoretical. NASA and other space agencies are actively developing them. Tests have been conducted, reactors designed, and missions planned. Nuclear propulsion could revolutionize space travel, making the outer planets accessible within a single human lifetime and opening the possibility of journeys to nearby stars. The challenge lies not in the physics, which is well understood, but in the engineering and safety considerations. Building reactors that can operate reliably in the harsh environment of space requires meticulous design and testing. Yet the potential rewards, faster travel times, access to distant worlds, make it a goal worth pursuing. Solar sails and light propulsion. Another elegant method of propulsion relies not on fuel, but on light itself. Solar sails are vast, ultra-thin sheets of reflective material that catch photons from the sun. Though individual photons carry minuscule momentum, the cumulative effect of billions striking the sail can accelerate a spacecraft. The acceleration is gentle but continuous, and over time, a solar sail can reach impressive speeds without consuming any fuel. The concept was once pure science fiction, but it has become reality. In 2010, Japan's Icaros spacecraft deployed a solar sail and successfully used it to navigate through space. More ambitious projects are in development, including missions to intercept interstellar objects passing through our solar system. Some visionaries propose using powerful lasers to propel tiny spacecraft to nearby stars, accelerating them to a significant fraction of light speed. Solar sails represent a fundamentally different approach to space travel, one that harnesses the natural resources of the cosmos. Sunlight is abundant and free, and a sail requires no complex machinery. just material and patience. For missions that do not require speed, where the journey can unfold over years or decades, solar sails offer a graceful and efficient way to traverse the void. The dream of interstellar travel. The stars beyond our solar system are unimaginably distant. The nearest, Proxima Centauri, is over 4 light-years away. With current technology, reaching it would take tens of thousands of years. Yet humanity dreams of making that journey, of stepping onto worlds orbiting alien suns. Interstellar travel remains firmly in the realm of theory, but theories are where all great journeys begin. Several concepts have been proposed. Generation ships, massive vessels that would house entire communities, traveling for centuries while multiple generations live and die aboard. Suspended animation, placing travelers in a state of hibernation to survive the long voyage. Antimatter propulsion, harnessing the most energetic reactions known to physics. Each concept faces enormous challenges, but none violate the laws of physics. They are difficult, not impossible. The Breakthrough Starshot initiative proposes a different approach, sending tiny, lightweight probes, accelerated by ground-based lasers, to a fraction of light speed. These probes could reach Proxima Centauri in 20 years, sending back images and data from another star system. While this would not carry humans, it would be humanity's first tangible step toward the stars, proof that interstellar travel is achievable. For now, the stars remain distant lights in the night sky. But every great journey begins with a single step, and humanity has shown time and again that what seems impossible can become routine. The same species that once thought the sky was an impenetrable barrier now lives among the stars in orbit. The dream of interstellar travel may take centuries to realize, but it is a dream worth holding, a vision that inspires and challenges us to reach ever farther. Space tourism begins. In 2001, American businessman Dennis Tito paid $20 million to spend 8 days aboard the International Space Station, becoming the first space tourist. His journey marked the beginning of a new era, one where space was not just for trained astronauts, but for anyone with the resources and desire to go. Since then, a handful of others have followed, paying for trips to orbit, experiencing weightlessness, and gazing down at Earth from above. In recent years, space tourism has expanded. Companies like SpaceX, Blue Origin, and Virgin Galactic offer flights that reach the edge of space, providing a few minutes of weightlessness and views of Earth's curvature. These suborbital flights are brief, but they give passengers a taste of what astronauts experience. The cost is still high, hundreds of thousands of dollars, but it is dropping as technology improves and competition increases. The long-term vision is more ambitious. Orbital hotels, lunar resorts, even trips around the moon. While these remain years away, the infrastructure is being built. Private space stations are in development, designed specifically for tourism and research. As access to space becomes more routine, the experience will become available to more people. Space tourism is not just about adventure. It is about changing our perspective, seeing Earth as a fragile oasis in the vastness of space, a view that astronauts describe as profoundly transformative. The overview effect. Astronauts who have traveled to space often describe a powerful emotional experience called the overview effect. From orbit, Earth appears as a small, fragile sphere floating in the blackness. The thin blue line of the atmosphere is visibly delicate, the only barrier between life and the void. Borders between nations are invisible. The planet looks unified, a single, interconnected system. This perspective shifts how astronauts see humanity. Conflicts that seem important on the ground appear trivial from above. The realization that we all share one planet, with no backup, becomes visceral. Many astronauts return with a renewed commitment to environmental protection, peace, and cooperation. They speak of feeling a deep connection to all life on Earth, a recognition of our shared destiny. The overview effect is not just for astronauts. As more people travel to space through tourism, more will experience this shift in perspective. Photographs and videos from orbit have already brought a taste of it to billions. The iconic Earthrise image from Apollo 8, showing Earth rising above the Moon's horizon, helped inspire the environmental movement. The more we see our world from space, the more we may come to appreciate its beauty and fragility, and the more we may work to preserve it. Asteroid mining. The asteroids that orbit the Sun between Mars and Jupiter contain vast resources. Metals like iron, nickel, and platinum exist in concentrations far higher than on Earth. Water ice, trapped in some asteroids, could be broken down into hydrogen and oxygen for rocket fuel. Mining these resources could provide the raw materials for building spacecraft, habitats, and infrastructure in space, reducing the need to launch everything from Earth. Several companies have been founded with the goal of mining asteroids. The technical challenges are significant: identifying suitable targets, reaching them, extracting materials in microgravity, and transporting them back. But the potential rewards are enormous. A single large asteroid could contain more platinum than has ever been mined on Earth. The economic value is staggering, potentially trillions of dollars. Beyond economics, asteroid mining could enable deeper space exploration. Fuel produced from asteroid water could be stored at depots throughout the solar system, creating a network of refueling stations. Spacecraft could travel farther without carrying all their fuel from Earth, making missions to the outer planets more feasible. Asteroid mining is still in its infancy, but it represents a future where space is not just a destination, but a source of resources, a place where industry and exploration converge. The challenge of space debris. Decades of space activity have left a legacy in orbit. Debris, defunct satellites, spent rocket stages, fragments from collisions and explosions, all circle Earth at high speeds. There are millions of pieces, ranging from tiny flecks of paint to entire dead satellites. Even small debris is dangerous. At orbital velocities, a fragment the size of a marble can puncture a spacecraft or destroy a satellite. The problem is growing. Each collision creates more debris, which increases the likelihood of further collisions, a cascade known as Kessler syndrome. If unchecked, it could render certain orbits unusable, trapping humanity on Earth. Tracking debris is essential, and space agencies monitor thousands of objects to predict and avoid collisions. The ISS has maneuvered multiple times to dodge debris. Solutions are being developed. Concepts include nets, harpoons, and lasers to capture or deflect debris, and spacecraft designed to deorbit large pieces safely. Some satellites are now built to deorbit themselves at the end of their missions, burning up in the atmosphere. Cleaning up space is a shared responsibility, requiring international cooperation. The orbital environment must be managed carefully if future generations are to continue exploring and utilizing space. Lunar bases. Establishing a permanent base on the Moon is a goal that has captivated planners for decades. Unlike short Apollo visits, a lunar base would be occupied continuously, serving as a research station, a testbed for technologies needed on Mars, and potentially a hub for mining and manufacturing. The Moon's south pole, with its ice deposits and areas of near-constant sunlight, is the leading candidate for such a base. Living on the Moon presents unique challenges. The lunar day lasts 2 weeks, followed by 2 weeks of night. Temperatures swing from boiling during the day to far below freezing at night. There is no atmosphere, so protection from radiation and micrometeorites is essential. Habitats would need to be robust, possibly buried under lunar soil for added shielding. But the Moon also offers advantages. Its gravity, 1/6 of Earth's, makes it easier to launch spacecraft. Resources like water, ice, and regolith can be used to produce fuel, oxygen, and building materials. A lunar base could support telescopes on the far side, shielded from Earth's radio noise, providing unparalleled views of the universe. The Moon is only 3 days away, close enough for relatively quick resupply and evacuation if needed. It is the perfect proving ground for learning to live off-world. Martian colonies. Mars represents the ultimate challenge for human settlement. Building a colony there would require overcoming obstacles that dwarf those of the Moon. The thin atmosphere provides some protection, but not enough to breathe or shield against radiation. The cold is severe, with average temperatures around -60 degrees Celsius. Dust storms can engulf the entire planet for months. Yet Mars has resources. Water ice exists beneath the surface and at the poles. The atmosphere, though thin, contains carbon dioxide, which can be processed into oxygen and methane. Martian soil, properly treated, might support agriculture. The day length, just slightly longer than Earth's, is compatible with human circadian rhythms. These factors make Mars the most viable candidate for a self-sustaining human presence beyond Earth. Early Martian colonies would be small, perhaps a dozen people living in pressurized habitats, conducting research and testing technologies. Over time, they would expand, mining resources, manufacturing goods, and growing food. The goal would be self-sufficiency, reducing dependence on Earth. Eventually, a Martian colony could grow into a true settlement, a place where children are born and raised, where a new branch of human civilization takes root. It is an audacious vision, but one that lies within the realm of possibility if we commit the resources and will to achieve it. Terraforming Mars. Some envision an even more ambitious future for Mars, transforming it into a world more like Earth, a process called terraforming. The idea is to warm the planet, thicken its atmosphere, and eventually allow liquid water to flow on the surface, creating conditions where humans could walk outside without spacesuits. Proposed methods include releasing greenhouse gases to trap heat, positioning mirrors in orbit to reflect sunlight onto the surface, or even crashing comets into the planet to deliver water. These processes would take centuries or millennia, requiring sustained effort across generations. Whether it is even possible remains uncertain. Mars lacks a strong magnetic field to protect a thickened atmosphere from being stripped away by solar wind. Terraforming raises profound questions. Should we alter an entire planet, potentially destroying any native life that might exist, to suit our needs? Is it ethical to commit future generations to such a project? Or is it humanity's destiny to spread life throughout the solar system, transforming barren worlds into gardens? These are debates without easy answers. For now, terraforming remains in the realm of speculation, a dream that challenges our imagination and our understanding of what it means to be stewards of worlds. The legacy of Voyager. In 1977, 2 spacecraft left Earth on a mission to explore the outer planets. Voyager 1 and Voyager 2 exceeded every expectation, sending back the first close-up images of Jupiter, Saturn, Uranus, and Neptune. They revealed active volcanoes on Jupiter's moon Io, intricate rings around Saturn, and geysers on Neptune's moon Triton. They transformed our understanding of the outer solar system. After completing their planetary tours, the Voyagers continued outward. In 2012, Voyager 1 crossed the heliopause, the boundary where the sun's influence fades, entering interstellar space. Voyager 2 followed in 2018. They are now the most distant human-made objects, billions of miles away, still transmitting faint signals back to Earth. Their power will eventually run out, expected sometime in the 2030 seconds, and they will go silent, but they will continue drifting through the galaxy for billions of years. Each Voyager carries a golden record, a phonograph disc containing sounds and images from Earth, music, greetings in dozens of languages, the cries of whales, the laughter of children. It is a message to the cosmos, a declaration that we exist and that we reached out. The chance of anyone finding these records is vanishingly small, but that is not the point. The Voyagers are a testament to human curiosity, a symbol of our drive to explore and understand. They remind us that even the smallest steps can carry us far beyond what we imagined. The New Horizons mission. In 2006, NASA launched New Horizons, a spacecraft bound for Pluto. For 9 years, it traveled across the solar system, covering more than 3 billion miles. In July 2015, it flew past Pluto, capturing the first detailed images of the distant dwarf planet. The images revealed a world far more complex and beautiful than anyone anticipated. Pluto's surface showed mountains of water ice, plains of frozen nitrogen, and a heart-shaped region that captured the public's imagination. After Pluto, New Horizons continued deeper into the Kuiper Belt, a region beyond Neptune filled with icy bodies left over from the solar system's formation. On the 1st of January 2019, it flew past Arakoth, a small, snowman-shaped object. It was the most distant flyby ever conducted, over 4 billion miles from Earth. The images showed a pristine, ancient world, untouched since the solar system's birth. New Horizons demonstrated that even the most distant reaches of the solar system are within our grasp. It inspired a generation with images of worlds previously seen only as blurry dots. And it continues onward, sending back data as it travels farther into the unknown. Every mission, like New Horizons, expands the boundaries of exploration, reminding us that there is always more to discover. The Parker Solar Probe. While some missions venture to the solar system's edge, others journey toward its heart. The Parker Solar Probe, launched in 2018, is designed to study the Sun up close, closer than any spacecraft before it. It will eventually pass within 4 million miles of the Sun's surface, enduring temperatures over 2,000 degrees Fahrenheit. A heat shield protects its instruments, allowing it to gather data on the Sun's corona, the outer atmosphere that is mysteriously hotter than the surface itself. Parker's mission is to solve long-standing mysteries about the Sun. Why is the corona so hot? How does the solar wind accelerate? What drives solar flares and coronal mass ejections? These phenomena affect Earth, disrupting satellites, power grids, and communication systems. Understanding them could help us predict space weather and protect our technology. The probe's journey is a series of flybys, using Venus's gravity to gradually bring it closer to the Sun. Each pass gathers more data, building a comprehensive picture of our star. Parker represents the extremes of engineering, designing a spacecraft that can survive where nothing human-made has ventured before. It reminds us that exploration is not just about distant worlds, but also about understanding the forces that shape our own. Communication across the void. As spacecraft travel farther from Earth, communication becomes increasingly challenging. Radio signals, traveling at the speed of light, take minutes to reach Mars and hours to reach the outer planets. Voyager 1's signal, transmitted from interstellar space, takes over 22 hours to reach Earth. commands sent to distant spacecraft require patience. By the time a signal arrives, the spacecraft may have moved or conditions changed. NASA's Deep Space Network, a collection of giant radio antennas located around the world, maintains contact with distant missions. These antennas are sensitive enough to detect the faint whisper of a spacecraft billions of miles away. Signals so weak they carry less power than a snowflake hitting the ground. Maintaining this link requires precision and dedication, but it is essential. Without communication, spacecraft would be lost, their discoveries never known. Future missions may rely on laser communication, which can transmit more data over greater distances. Tests are underway, and the technology promises to revolutionize how we stay connected with explorers venturing to the edge of the solar system and beyond. Communication is the thread that binds us to our robotic ambassadors, ensuring that their journeys of discovery enrich all of humanity. The role of artificial intelligence. Modern space exploration increasingly relies on artificial intelligence. Rovers on Mars cannot be controlled in real time. The communication delay makes it impossible. Instead, they are programmed to navigate autonomously, identifying obstacles, selecting paths, and even choosing which rocks to study. AI allows them to make decisions on their own, maximizing the science they can accomplish. Spacecraft use AI for navigation, adjusting their trajectories to compensate for unexpected conditions. Future missions to distant moons and asteroids will depend even more on autonomy. Human operators cannot react quickly enough when light minutes or light hours of delay separate them from their craft. AI must be trusted to handle emergencies, conduct observations, and ensure mission success. There is something poetic about this. Humanity's creations, imbued with intelligence, venture into the cosmos on our behalf. They are extensions of our curiosity, our eyes and minds exploring places we cannot yet reach. As AI becomes more sophisticated, these machines may become true partners in exploration, making discoveries and decisions that expand the frontiers of knowledge. The international nature of space exploration. Space exploration has always been international in spirit, even when driven by competition. The International Space Station is the most visible symbol of cooperation, with astronauts from dozens of countries living and working together. But collaboration extends far beyond the ISS. Missions often involve multiple nations contributing instruments, expertise, or funding. Data from space missions is shared freely, enriching the global scientific community. This cooperation is pragmatic. Space exploration is expensive and complex, and no single nation can do everything alone. But it is also idealistic, reflecting a vision of humanity united in pursuit of knowledge. When astronauts from different countries work together in orbit, they demonstrate that collaboration can transcend politics. When nations pool resources to explore Mars or study the Sun, they show that our common goals can outweigh our differences. The future of space exploration will depend on continued cooperation. Missions to Mars, lunar bases, and ventures to the outer planets will require international partnerships. Treaties and agreements will need to address how resources are shared, how space is governed, and how we prevent conflict in the final frontier. Space offers humanity a chance to build a better model of cooperation, one based on shared curiosity and mutual benefit. Women in space. The history of space exploration has often overlooked the contributions of women, but they have been there from the beginning. In 1963, Soviet cosmonaut Valentina Tereshkova became the first woman in space, orbiting Earth 48 times. It would be nearly 20 years before another woman followed. In 1983, Sally Ride became the first American woman in space, flying aboard the Space Shuttle Challenger. Since then, women have played increasingly prominent roles. They have commanded space shuttles, conducted spacewalks, and lived aboard the ISS for extended periods. Astronauts like Peggy Whitson and Christina Koch have set records for time in space and all-female spacewalks. Women have also contributed as engineers, scientists, and mission controllers, their expertise essential to every mission's success. NASA's Artemis program aims to land the first woman on the moon, a symbolic milestone, but also a reflection of progress. The future of space exploration will be inclusive, drawing on the talents of all humanity. As we venture farther from Earth, diversity will be a strength, bringing different perspectives and skills to the challenges ahead. The stars belong to everyone, and the journeys we take to reach them should reflect the richness of the human experience. Protecting planetary environments. As we explore other worlds, we must consider our impact on them. Planetary protection is the practice of preventing contamination, both bringing Earth microbes to other worlds and bringing extraterrestrial material back to Earth. This is not just about preserving alien environments. It is about ensuring that if we find signs of life, we can be certain they are truly alien and not hitchhikers from home. Spacecraft bound for Mars or other potentially habitable worlds are sterilized before launch. Clean rooms, heat treatment, and careful assembly minimize the risk of contamination. Missions that return samples from other worlds, like those planned for Mars, will quarantine the material, studying it in secure facilities to ensure it poses no risk. These precautions reflect a growing ethical awareness. Other worlds, even barren ones, have value beyond their utility to us. They are natural laboratories, records of the solar system's history, and potentially homes to life. As we explore, we must balance our curiosity with responsibility, ensuring that our presence does not destroy what we seek to understand. The pale blue dot. In 1990, as Voyager 1 journeyed beyond Neptune, it turned its camera back toward Earth one last time. From nearly 4 billion miles away, it captured an image showing Earth as a tiny speck, a pale blue dot suspended in a beam of scattered sunlight. Astronomer Carl Sagan, reflecting on this image, wrote words that have resonated ever since. He spoke of how that dot contained everyone we have ever known, every human who has lived, loved, suffered, and died. All of history, every triumph and tragedy, played out on that mote of dust. The image reminds us of our smallness, of how fragile and precious Earth is. It invites humility, a recognition that our conflicts are petty when viewed from the perspective of the cosmos. The pale blue dot is more than a photograph. It is a call to cherish our world and each other. It reminds us that, for now, Earth is our only home, and we must care for it. But it also inspires us to reach beyond, to explore, to ensure that life, in all its beauty and complexity, spreads to other worlds. The image is both a grounding and an invitation, a reminder of where we are and a vision of where we might go. The cost of exploration. Space exploration is expensive. Missions cost billions of dollars, and the benefits are not always immediate or tangible. Critics argue that this money could be better spent addressing problems on Earth: poverty, disease, climate change. It is a fair question. Why spend so much reaching for the stars when there is so much need here? The answer lies in the long-term value of exploration. Space technology has given us satellite communication, GPS, weather forecasting, and countless innovations that improve daily life. The challenges of space push us to develop new materials, new methods, new ways of thinking. The knowledge we gain about our planet, our solar system, and the universe, enriches our understanding of existence itself. But beyond the practical, there is something deeper. Exploration is part of what makes us human. It has driven us to cross oceans, climb mountains, and venture into the unknown throughout history. It inspires us, challenges us, and unites us. The dream of reaching other worlds gives us hope, a vision of a future where humanity thrives beyond Earth. That vision, that hope, has value that cannot be measured in dollars alone. Living in microgravity, one of the strangest aspects of spaceflight is weightlessness. In orbit, astronauts float freely, not because there is no gravity, Earth's pull is still strong at the ISS's altitude, but because they are in constant free fall, moving sideways fast enough that they keep missing the planet. This state of microgravity affects every aspect of life. Simple tasks become complicated. Eating requires food to be sticky or packaged to prevent it from floating away. Drinking is done through straws from sealed bags. Sleeping is disorienting. Without a sense of up or down, astronauts strap themselves into sleeping bags attached to walls. Exercise is essential to prevent muscle and bone loss. Astronauts spend hours each day on treadmills and resistance machines, held down by bungee cords. The human body adapts to microgravity in surprising ways. Fluids shift toward the head, causing a puffy face and making astronauts feel congested. The spine elongates, making people temporarily taller. Without the constant pull of gravity, bones lose density and muscles atrophy. These changes are mostly reversible, but long-duration missions will require countermeasures to keep astronauts healthy. Understanding microgravity is essential for future journeys to Mars and beyond. The psychological challenge of isolation space is not just a physical challenge, but a psychological one. Astronauts on long missions face isolation, confined to small spaces with the same few people for months. They are far from family and friends, with communication delays that make real-time conversation impossible on missions to Mars. The environment is hostile, with no possibility of immediate rescue if something goes wrong. Psychologists study how astronauts cope, looking for traits that make someone resilient in these conditions. Strong interpersonal skills are crucial. Conflicts in a small, isolated crew can escalate quickly. So are hobbies and rituals that provide structure and comfort. Astronauts aboard the ISS watch movies, read, play musical instruments, and stay connected with loved ones through video calls. These small touches of normalcy help maintain mental health. Future missions will need to address these challenges proactively. Crews will be selected not just for technical skills, but for psychological compatibility. Virtual reality might provide mental escapes, allowing astronauts to experience simulations of Earth environments. Understanding and supporting mental health will be as important as any engineering challenge, ensuring that those who venture into space can thrive, not just survive. The future of space stations. The International Space Station has been continuously occupied since November 2000, but it will not last forever. Its modules are aging, and it is expected to be deorbited sometime in the 2030 seconds. What comes next? Several possibilities are in development. NASA has partnered with private companies to develop commercial space stations. These will be smaller than the ISS, but more modern, designed for research, manufacturing, and tourism. China is building its own station, Tiangong, with modules being launched and assembled in orbit. Other nations are considering their own platforms. The future may see multiple stations in orbit, each serving different purposes. Beyond Earth orbit, there is the Lunar Gateway, a station orbiting the Moon. Farther out, concepts exist for stations at Lagrange points, gravitationally stable locations where spacecraft can remain with minimal fuel. These could serve as waypoints for missions deeper into the solar system. The era of a single space station is giving way to a network of orbital outposts, each expanding our presence and capabilities in space. Mining the Moon. The Moon holds resources that could support both lunar bases and missions deeper into space. Water ice in permanently shadowed craters can be split into hydrogen and oxygen, providing fuel for rockets and life support for astronauts. Rare elements like helium-3, deposited by the solar wind over billions of years, could potentially fuel future fusion reactors. Mining the Moon is not science fiction, but a serious proposal. Several companies and space agencies are developing technologies to extract and process lunar resources. Robots would do the heavy lifting, drilling, and transporting material to processing facilities. The Moon's low gravity makes launching resources back into orbit much easier than from Earth, which could support construction of spacecraft and habitats in space. This vision raises questions. Who owns the Moon's resources? International treaties state that no nation can claim sovereignty over celestial bodies, but they are less clear about resource extraction. As lunar mining becomes feasible, these legal and ethical questions will need answers. The Moon could become a hub of economic activity, a place where humanity learns to live and work off-world, building the foundation for a spacefaring civilization. Fusion propulsion. One of the most promising technologies for deep space exploration is nuclear fusion. Unlike fission, which splits atoms, fusion combines them, the same process that powers the sun. Fusion releases enormous energy and produces far less radiation. If harnessed for propulsion, it could enable journeys to the outer planets in weeks rather than years, and make missions to nearby stars conceivable within human lifetimes. Fusion propulsion works by heating plasma to millions of degrees and using magnetic fields to direct it as exhaust. The technical challenges are immense. Fusion has proven difficult to achieve in controlled, sustained reactions, even on Earth, but progress is being made. Experimental reactors have achieved brief moments of fusion, and the technology inches closer to practicality. If fusion propulsion becomes reality, it will transform space exploration. Missions that currently take decades could be completed in a fraction of the time. The outer solar system, now remote and difficult to reach, would become accessible. Even journeys beyond, to the Oort cloud or neighboring star systems, would shift from theoretical to possible. Fusion represents the next great leap in propulsion, a technology that could unlock the galaxy. The search for technosignatures. While some search for microbial life, others look for signs of advanced civilizations. These are called technosignatures, evidence of technology created by intelligent beings. Radio signals, megastructures that alter a star's light, atmospheric pollution that could only come from industry. Finding any of these would prove that we are not alone and that intelligence is not unique to Earth. Projects like SETI, the search for extraterrestrial intelligence, scan the skies for radio signals that might be messages or leakage from alien technology. So far, they have found nothing conclusive, but the search continues. With more powerful telescopes and wider surveys, the chances improve. Each new exoplanet discovered is another potential source, another system where a civilization might exist. The discovery of a technosignature would be one of the most profound events in human history. It would mean that life not only exists elsewhere, but has evolved intelligence and technology. It would raise questions about our place in the cosmos, about whether we are young or old compared to others, about what the future might hold. Even if we never make contact, knowing we are not alone would change everything. The ethics of contact. If we ever encounter extraterrestrial intelligence, how should we respond? This question has been debated by scientists, philosophers, and ethicists. Some argue we should announce our presence loudly, broadcasting messages to the stars. Others urge caution, warning that advertising our existence could be dangerous. We do not know what is out there, whether potential neighbors are peaceful or hostile. There is also the question of cultural contamination. If we contact a less advanced civilization, would our presence disrupt their development? And what if we are the less advanced? Contact with a civilization thousands or millions of years ahead of us could be overwhelming, rendering our own technology and knowledge obsolete overnight. For now, these debates are theoretical. We have sent a few messages into space, like the Arecibo message transmitted in 1974, but we have received no response. Our own signals, radio and television broadcasts leaking into space, have spread only about 100 light-years, a tiny bubble in the vastness of the galaxy. If anyone is out there, they may not have noticed us yet, but the questions remain, waiting for the day when contact, if it happens, transforms them from speculation to reality. The long journey ahead, space exploration, is still in its infancy. We have taken the first steps, ventured beyond our atmosphere, walked on the moon, sent robots to distant worlds. But the cosmos is vast, and we have barely scratched its surface. The nearest star is 4 light-years away. The Milky Way stretches 100,000 light-years across. And beyond our galaxy lie billions more, each containing billions of stars. The journey ahead will take generations. Technologies we can barely imagine will be needed. Collaboration across nations, across cultures, across time. The challenges are immense, but so are the rewards. Every new world we reach expands our understanding, our possibilities. Every discovery, whether a new moon, a distant galaxy, or the first signs of life beyond Earth, adds to the grand tapestry of knowledge. Space exploration is not just about reaching destinations. It is about the journey itself, the questions we ask, the problems we solve, the ways we grow. It is about ensuring that humanity's story does not end on a single world, but continues, spreading across the stars, carrying with it the curiosity, creativity, and hope that define us. The sounds of space. Space is often described as silent, a vacuum where sound cannot travel. This is true in the traditional sense. Without air or other medium to carry vibrations, there are no sounds as we know them. Astronauts in spacewalks report complete silence, broken only by their own breathing and the voices of colleagues transmitted through radio. Yet space is not without its music. Planets and stars emit electromagnetic radiation across many frequencies. Scientists have converted these emissions into audio, creating eerie soundscapes. Jupiter's magnetosphere produces whistles and pops. Saturn's rings create a gentle hiss as particles collide. Pulsars send out regular beeps like cosmic lighthouses. Even black holes have been given voice, their gravitational waves translated into deep, resonant tones. These sounds are not merely curiosities. They carry information about the objects that produce them. By listening to space, translated through instruments and computers, scientists can study phenomena invisible to telescopes. The symphony of the cosmos plays constantly, a concert of radio waves, X-rays, and magnetic fields. We cannot hear it directly, but through technology, we have learned to appreciate its strange beauty. Training to be an astronaut, becoming an astronaut, requires years of rigorous preparation. Candidates must have advanced degrees in science or engineering, often with military or test pilot experience. The selection process is intensely competitive. NASA receives thousands of applications for each astronaut class and selects only a handful. Those chosen undergo training that pushes them to their physical and mental limits. Physical fitness is essential. Astronauts train underwater in giant pools, wearing spacesuits to simulate the weightlessness of spacewalks. They practice tasks repeatedly, learning to work efficiently in bulky gloves while floating. They experience high g-forces in centrifuges, preparing for the intense acceleration of launch. They fly in aircraft that create brief periods of weightlessness, parabolic arcs that earn the plane its nickname, the Vomit Comet. But technical skills are only part of preparation. Astronauts learn Russian to communicate with cosmonauts aboard the ISS. They study spacecraft systems in exhaustive detail, memorizing procedures for normal operations and emergencies. They train in remote locations, Iceland, caves, deserts, learning to work as a team in harsh, isolated environments. By the time they fly, they have spent years preparing for every conceivable situation. The training is grueling, but it ensures they are ready for the challenges of space. The experience of launch. The moment of launch is unlike anything else. Astronauts lie strapped into their seats, feeling the rocket rumble to life beneath them. The countdown echoes in their helmets. Then ignition, and the world begins to shake. The force builds rapidly as the rocket accelerates, pushing astronauts back into their seats with mounting pressure. Within minutes, they are experiencing 3 times Earth's gravity, their bodies heavy, breathing difficult. The ride is violent. Vibrations rattle every bone. The roar of engines fills the cabin despite insulation. Then, abruptly, the solid rocket boosters separate, falling away. The acceleration smooths, but continues. The astronauts watch through windows as the sky outside transitions from blue to black, the atmosphere thinning. The main engines burn, pushing them faster, higher. 8.5 minutes after liftoff, the engines cut off. Suddenly, everything is silent and still. Objects that were pressed down by acceleration begin to float. Pencils, checklists, anything not secured drifts upward. The astronauts feel weightlessness for the first time, a sensation both strange and exhilarating. They have left Earth behind. They are in orbit, traveling at 17,000 miles per hour, yet feeling as though they are perfectly still. The journey has begun. Spacewalks. Stepping outside a spacecraft into the vacuum is one of the most dangerous and awe-inspiring experiences an astronaut can have. Spacewalks, formerly called extravehicular activities, or EVAs, require meticulous preparation. Astronauts spend hours breathing pure oxygen before the walk, purging nitrogen from their blood to prevent decompression sickness. They don their spacesuits, complex garments that provide oxygen, temperature control, and protection from radiation and micrometeoroids. Once outside, they are tethered to the spacecraft by cables, a lifeline that provides both safety and communication. The work is physically demanding. Even simple tasks require significant effort in the bulky suit. Astronauts replace equipment, install experiments, and repair systems, often working for 6 or 7 hours. The view is stunning. Earth filling half the sky, the sun blazing without atmosphere to soften it, stars visible even in daylight. But spacewalks are risky. A punctured suit could be fatal. Tools can slip away, lost forever. Water once leaked into an astronaut's helmet, filling it and nearly drowning him before he could get back inside. Despite these dangers, spacewalks are essential. They allow repairs and upgrades that keep spacecraft functioning. And for those who perform them, the experience is unforgettable. A chance to float in the void with only a thin layer of fabric between them and infinity. The view from orbit. One of the most frequently mentioned experiences by astronauts is the sheer beauty of Earth from space. The planet is vibrant, a swirl of blues, greens, and whites. Oceans shimmer in sunlight. Continents show their varied landscapes, deserts in gold and brown, forests in deep green, mountain ranges casting shadows. Clouds form intricate patterns, spirals of hurricanes, wisps of cirrus, towering thunderstorms flashing with lightning. At night, cities glow like constellations, webs of light marking where humanity lives. Fishing fleets off the coast of Asia dot the ocean with their lamps. Wildfires appear as orange smudges. Auroras shimmer over the poles, curtains of green and red dancing in the thin upper atmosphere. And always, the thin blue line of the atmosphere is visible, a delicate shell that holds all life we know. Astronauts describe feeling a profound connection to Earth. From orbit, borders are invisible, conflict seems small, and the fragility of our world is apparent. This perspective stays with them. Many return as advocates for environmental protection and international cooperation. The view from orbit is more than beautiful. It is transformative, a reminder of what we share and what we stand to lose. Eating in space, food in space, has evolved significantly since the early days. Early astronauts ate from tubes, squeezing purees and pastes into their mouths. It was nutritious, but hardly appetizing. Today, meals are far better. Astronauts aboard the ISS enjoy a variety of foods, some freeze-dried and rehydrated, others thermostabilized in pouches, ready to eat after heating. Menus include everything from scrambled eggs to shrimp cocktail, from beef stew to apple pie. Fresh fruit and vegetables arrive with resupply missions, a welcome treat that doesn't last long. Astronauts can add condiments. Salt and pepper come in liquid form to prevent particles from floating away and clogging equipment. Eating is a social activity. Crews gather around a table, held in place by foot restraints, sharing meals and conversation. Taste is affected by microgravity. Fluids shift toward the head, causing congestion that dulls flavor. Many astronauts prefer spicier foods to compensate. Despite the challenges, mealtime provides normalcy, a break from work, a chance to relax. Food is also psychological comfort, a reminder of home. Some astronauts bring favorite snacks, small tastes of Earth to savor, while floating hundreds of miles above it. Sleeping in orbit, sleep in space, is disorienting at first. Without gravity, there is no up or down, no sensation of lying in bed. Astronauts sleep in small crew quarters, little more than phone booths with sleeping bags attached to the wall. They zip themselves in to avoid drifting. Some strap their arms down, others let them float upward, waking to find them hovering in front of their faces. The ISS orbits Earth every 90 minutes, meaning the sun rises and sets 16 times a day. To maintain a regular schedule, astronauts follow Earth time, with lights dimmed for night. But the constant cycle can make sleep difficult. Shades cover windows to block sunlight. Earplugs and eye masks help. Even so, many astronauts report sleeping less in space than on Earth. Dreams in space are said to be vivid. Some astronauts dream they are falling, waking in confusion, before remembering they are already falling, perpetually around the planet. Others dream of flying, a sensation that mirrors the reality of weightlessness. Sleep is essential for health, and researchers study how to improve it, developing better schedules, lighting, and sleeping quarters. Rest is as important in space as on Earth, perhaps more so given the demands of life in orbit. Returning to Earth. Coming home is not a gentle process. When astronauts are ready to return, they board their capsule and seal the hatch. Retro rockets fire, slowing the spacecraft enough for it to drop out of orbit. As it enters the atmosphere, friction heats the heat shield to thousands of degrees. The capsule glows like a meteor, plasma streaming past the windows, radio communications blacked out by ionized gases. The deceleration is intense. Astronauts experience up to 4 times Earth's gravity, pressed hard into their seats after months of weightlessness. The heat, noise, and shaking are overwhelming. Then parachutes deploy, jerking the capsule upright, slowing its descent. It drifts down, swaying beneath the canopy, until it splashes into the ocean or thumps onto land. Recovery teams rush to assist, opening the hatch and helping astronauts out. Readjusting to gravity is difficult. After months in space, astronauts' muscles and bones have weakened. Standing feels strange, heavy. Some need help walking at first. They undergo medical checks and begin rehabilitation, exercising to rebuild strength. The transition takes weeks, but gradually they adapt. The experience of space stays with them, a memory of floating freely, of seeing Earth from above, of living among the stars. Space medicine. Keeping astronauts healthy in space requires specialized medicine. Microgravity affects the body in unexpected ways. Bones lose density at a rate of 1 to 2% per month. Muscles atrophy despite daily exercise. Fluid shifts cause vision problems in some astronauts, pressure building behind the eyes. Radiation exposure increases cancer risk, especially on missions beyond Earth's protective magnetic field. Doctors monitor astronauts closely. Blood and saliva samples are collected regularly. Ultrasounds check for changes in the heart and blood vessels. Astronauts follow strict exercise regimens, spending 2 hours a day on treadmills and resistance machines to counteract muscle and bone loss. Nutrition is carefully managed to ensure adequate calcium, vitamin D, and other nutrients. Treating illness or injury in space is challenging. The ISS has a small medical kit, but serious problems require evacuation to Earth, a process that takes hours and is risky in itself. Future missions to Mars will be too far for quick return, so spacecraft will need more advanced medical capabilities, perhaps even surgical facilities. Telemedicine helps, with doctors on Earth guiding astronauts through procedures via video link. Space medicine is a growing field, essential for enabling longer missions and eventual settlement beyond Earth. The cost of weightlessness. Living in microgravity takes a toll. Beyond bone and muscle loss, astronauts face other health challenges. The immune system weakens, making infections more likely. Wounds heal more slowly. The cardiovascular system adapts to the reduced workload. The heart grows slightly smaller, and blood pressure drops. These changes are mostly reversible, but they accumulate over time. Vision changes are particularly concerning. Nearly 2/3 of astronauts experience some vision degradation during long missions. Fluid pressure in the skull increases, pushing on the optic nerve and flattening the eyeball. Some astronauts need stronger glasses, both during their mission and after returning. Researchers are studying countermeasures, from exercise devices that create artificial gravity through centrifugal force, to dietary supplements that might reduce fluid pressure. Radiation is another serious risk. Earth's magnetic field shields us from much of the sun's radiation and cosmic rays. But in space, astronauts receive far higher doses. This increases cancer risk, especially for missions beyond low Earth orbit. Shielding helps, but it adds weight, and no practical amount can block all radiation. Future spacecraft may include dedicated shelters, areas with extra shielding where crews can retreat during solar storms. Understanding and mitigating these risks is essential for long-duration missions. Growing food in space. For short missions, bringing food from Earth is practical. But for long journeys to Mars or permanent settlements, growing food in space becomes essential. The ISS has served as a testbed for space agriculture. Astronauts have grown lettuce, radishes, peppers, and even flowers, learning what works in microgravity. Plants grow differently without gravity. Roots don't naturally grow downward, so special systems guide them. Water doesn't drain, so hydroponic methods, growing plants in nutrient-rich water, work better than soil. Lighting must be carefully controlled. LED arrays provide the specific wavelengths plants need for photosynthesis. Air circulation is crucial to prevent pockets of carbon dioxide from building up around leaves. The harvests are small but significant. Fresh food boosts morale and provides nutrition that packaged meals can't match. It also represents self-sufficiency, a step toward independence from Earth. Future missions will need larger growing areas, perhaps entire modules dedicated to agriculture. Potatoes, wheat, soybeans, and other staples will need to be cultivated. Growing food in space is not just about sustenance. It is about creating sustainable habitats, places where humans can truly live, not just survive. Robotic companions, astronauts on the ISS, are not alone. They share their space with robots. Some are external, like Canadarm2, a robotic arm over 50 feet long that grasps visiting spacecraft and moves equipment during spacewalks. Others work inside. Simon, a floating sphere with a screen displaying a simple face, uses AI to assist astronauts, answering questions and providing instructions. These robots are valuable helpers. They perform tasks too dangerous or tedious for humans. They don't need rest, food, or air. Some are designed to inspect the outside of the station, checking for damage. Others run experiments, carrying out procedures with precision. As AI advances, these robots become more capable, learning from experience and making decisions autonomously. The relationship between astronauts and robots is evolving. Early machines were tools, operated directly by humans. Modern robots are more like colleagues, capable of independent action. Future missions may rely heavily on robots, especially in the early phases of colonization. Robots could build habitats, mine resources, and prepare sites before humans arrive. They extend our reach, allowing us to accomplish more than we could alone. In the vast loneliness of space, they may even become companions. The danger of radiation beyond Earth's protective magnetic field. Space is filled with radiation. The sun emits a constant stream of charged particles. The solar wind. Occasionally, it releases more intense bursts during solar flares and coronal mass ejections. Then there are galactic cosmic rays, high-energy particles from supernovae and other violent events across the galaxy. These particles can penetrate spacecraft hulls and human bodies. The effects range from minor to severe. Low doses increase cancer risk over time. Higher doses cause acute radiation sickness, nausea, fatigue, and immune system damage. The most energetic particles can even cause electronic equipment to malfunction. Protecting astronauts is a major challenge. Water and hydrogen-rich materials make effective shielding, but they are heavy. Some designs propose surrounding crew quarters with water tanks that double as radiation shields. Timing missions to avoid solar storms helps. Space weather forecasts track the sun's activity, warning of dangerous eruptions. On Mars or the Moon, astronauts could retreat to shelters buried under soil, which provides excellent protection. Understanding radiation and developing countermeasures is critical for human exploration beyond low Earth orbit. Without solutions, long missions carry unacceptable risks. But with proper precautions, those risks can be managed. The mechanics of orbital rendezvous docking, two spacecraft in orbit, is a delicate dance. It requires precise calculations and skilled piloting. When a capsule launches to rendezvous with the ISS, it doesn't fly directly toward the station. Instead, it enters an orbit below the station and gradually catches up. As it approaches, thrusters fire to adjust speed and trajectory, bringing it closer. The final approach is slow and careful. The two spacecraft must match velocities exactly, moving in perfect synchrony as they drift together. Cameras and sensors guide the process, showing alignment and distance. When contact is made, docking mechanisms engage, pulling the spacecraft together and creating an airtight seal. Hatches open, and the crews can move between vehicles. Orbital mechanics are counterintuitive. Speeding up to catch another spacecraft can actually cause you to rise into a higher, slower orbit, falling behind. Slowing down drops you into a lower, faster orbit. Pilots must think in 3 dimensions, accounting for orbital paths that curve around the planet. Early rendezvous missions were tense, with astronauts learning these principles through trial and error. Today, computers assist, but the human touch remains essential. Docking is routine now, but it is still a marvel of precision. Micrometeoroid threats. Space is not empty. Tiny particles, fragments of asteroids and comets, zip through the solar system at tens of thousands of miles per hour. These micrometeoroids are often no larger than grains of sand, but at orbital speeds, they carry immense energy. A collision can puncture spacecraft hulls, damage solar panels, or shatter windows. The ISS is hit regularly. Small impacts pit the surface, leaving tiny craters. Most cause no harm. The station's shielding is designed to withstand them, but larger particles are a concern. Windows have been chipped, requiring shutters to protect them. Spacewalking astronauts face the risk of being struck, though their suits have multiple layers for protection. Detecting micrometeoroids is difficult. They are too small to track, appearing without warning. Spacecraft are designed with redundancy, multiple layers of shielding and backup systems in case of damage. Future missions to asteroids or the outer planets will face this threat constantly. It is one of the many invisible dangers of space, a reminder that beyond Earth's protective atmosphere, the environment is hostile and unforgiving. The colors of planets. Each planet in the solar system has its own distinct appearance, a result of its composition and atmosphere. Mercury is gray, its rocky surface baked by the sun. Venus is shrouded in thick, yellowish clouds of sulfuric acid. Earth, of course, is blue and white, oceans and clouds dominating. Mars is rusty red, iron oxide dust covering its surface. The gas giants are more colorful. Jupiter displays bands of cream, orange, and brown, swirling storms creating intricate patterns. Saturn is pale gold, its subdued hues hiding underlying complexity. Uranus is a serene blue-green methane in its atmosphere, absorbing red light. Neptune is a deeper blue, with dark storms and wispy white clouds. These colors are not just aesthetic, they reveal chemistry. The reds of Mars and Jupiter come from iron and sulfur compounds. The blues of Uranus and Neptune come from methane. By studying colors, scientists learn about atmospheres, surfaces, and the processes shaping these worlds. Each planet is a unique experiment in planetary formation, and their colors are clues to their histories. The silence of space. In movies, spaceships roar and explosions boom. In reality, space is utterly silent. Sound requires a medium to travel through: air, water, or solid material. In the vacuum of space, there is nothing. Events happen without noise. A meteoroid striking a spacecraft makes no sound. A thruster firing is silent to anyone outside. This silence is both eerie and peaceful. Astronauts describe it as profound, a quietness unlike anything on Earth. Inside spacecraft, there is noise, fans circulating air, pumps moving coolant, the hum of electronics. But outside, nothing. Communication happens via radio, electromagnetic waves that don't require air. Without it, astronauts would be isolated, unable to speak to each other, even if they were side by side in open space. The silence emphasizes the emptiness. Space is mostly void, vast distances separating objects. Sound would be useless there. Yet in that silence, there is beauty. It allows for a kind of contemplation, impossible amid the noise of Earth. For those who experience it, the silence of space is something they remember forever, a reminder of how different the universe is from the world we know. The legacy of the Hubble telescope. Few scientific instruments have captured the public imagination like Hubble. Its images grace textbooks, posters, and computer screens worldwide. The pillars of creation, towering columns of gas and dust where stars are born. The Hubble Deep Field, revealing thousands of galaxies in a patch of sky no larger than a pinhead held at arm's length. These images are not just scientifically valuable, they are art, beauty rendered by the universe itself. Hubble has also made critical discoveries. It measured the rate of the universe's expansion with unprecedented precision, helping determine that the universe is nearly 14 billion years old. It observed supernova in distant galaxies, revealing that the expansion is accelerating, driven by mysterious dark energy. It detected the atmospheres of exoplanets, analyzing their composition by watching how they filter their star's light. After more than 30 years in orbit, Hubble continues to function, though it has required multiple servicing missions by space shuttle astronauts to replace failing parts and upgrade instruments. Its successor, the James Webb Space Telescope, surpasses it in some ways, but Hubble remains operational, its unique capabilities still valuable. It is a testament to human ingenuity and the enduring desire to understand the cosmos. The concept of space elevators. One of the most ambitious concepts for reaching space is the space elevator. Instead of rockets, imagine a cable stretching from Earth's surface to orbit, tens of thousands of miles long. Vehicles would climb the cable, pulled by electric motors. The energy cost would be a fraction of a rocket launch, and there would be no need for fuel. It sounds like science fiction, but the physics are sound. The challenge lies in materials. The cable must be incredibly strong and light. Carbon nanotubes have the necessary properties, but manufacturing them at the required scale is beyond current capabilities. The cable would also need to withstand wind, lightning, and the danger of satellites or debris striking it. An anchor point in orbit, perhaps an asteroid, would provide counterbalance. If built, a space elevator would revolutionize access to space. Launching satellites, supplies, even people would become routine and affordable. It would enable large-scale construction of spacecraft in orbit and support for lunar and Martian colonies. For now, it remains a dream, but researchers continue exploring the concept, inching closer to making it reality. The space elevator represents a future where leaving Earth is as simple as taking an elevator. Space law and governance. As humanity expands into space, questions of law and governance arise. Who owns the moon? Can companies mine asteroids? What happens if debris from one nation's satellite damages another's? These issues are governed by international treaties, primarily the Outer Space Treaty of 1967, which states that space is the province of all humankind, and no nation can claim sovereignty over celestial bodies. But the treaty is vague on resource extraction and commercial activities. New agreements are needed as private companies become more active. The Artemis Accords, signed by multiple nations, attempt to address some issues, establishing principles for lunar exploration. But not all countries have signed, and disagreements remain. Conflict in space is a real concern. Satellites are vital for communication, navigation, and national security. Damaging or destroying them could have severe consequences. Preventing weaponization of space and ensuring peaceful cooperation will require ongoing diplomacy. As we venture farther, establishing fair and effective governance will be as important as developing the technology. Space belongs to everyone, and how we manage it will shape the future for generations. Imagining the first Martian colony picture, the first human settlement on Mars. A cluster of habitats, cylindrical modules half buried under Martian soil for radiation protection. Solar panels stretch across the red surface, and wind turbines harness the thin atmosphere. Greenhouses glow softly, filled with plants growing under LED lights. Rovers sit parked outside, covered in dust from recent excursions. Inside, a few dozen people live and work. They are scientists, engineers, and technicians, selected for their skills and their ability to thrive in isolation. Their days are filled with tasks: maintaining life support, conducting experiments, expanding the base. Communication with Earth is delayed by 20 minutes, so they must solve problems independently. They eat meals together, share stories, and watch sunsets where the sun appears half the size it does from Earth, the sky a dusty pink. Homesickness is a constant companion. They miss Earth's blue skies, the feel of wind and rain, the simple act of walking outside without a spacesuit. But they also feel pride. They are pioneers, laying the groundwork for a future where Mars is not just visited, but inhabited. Their children, if any are born there, will be the first generation of Martians, people who call another world home. The colony is small, fragile, but it is a beginning. Closing thoughts. And so, dear listener, our journey through the history and future of space travel comes to a close. From the first primitive rockets to visions of interstellar voyages, we have wandered together through humanity's greatest adventure. We have seen the courage of astronauts who risked everything to venture into the unknown, the ingenuity of engineers who turned dreams into reality, the dedication of scientists who peer ever deeper into the cosmos, seeking answers to the most profound questions. Space reminds us of our potential. It shows us that we are capable of extraordinary things when we work together, when we commit to a vision larger than ourselves. It humbles us, revealing our smallness in the vastness. And it inspires us, offering infinite possibilities, countless worlds to explore, and perhaps, one day, neighbors among the stars. As you lie here now, let your mind drift outward. Picture yourself floating in orbit, the curve of Earth below, the stars scattered above. Imagine standing on the rust-red surface of Mars, the pink sky stretching overhead. See yourself aboard a ship sailing past Saturn's rings, or drifting through the darkness between stars, traveling toward distant suns. The journey of space exploration is humanity's journey, and it is far from over. Each of us carries that pioneer spirit, that curiosity about what lies beyond the horizon. As we push outward, we carry with us the hopes and dreams of all who came before, and we light the way for those who will follow. The universe is vast and ancient, filled with wonders we are only beginning to understand. But it is also ours to explore, ours to cherish, ours to make home. Close your eyes now. Breathe deeply. Let the gentle pull of sleep carry you into dreams of distant worlds and starry skies. Rest well, traveler. The cosmos waits, patient and eternal, ready for the next chapter of our shared story. Good night.